And welcome to today's session. So we will start with some questions and doubts again. Yeah, Aditya, I will go through the questions and I will get back to you about them. Okay. So we will start with some question related with viscosity. The surface tension and viscosity. Some people had requested focus on that. So let's look at a question based on surface tension concept first. So we have a narrow capillary such that a certain liquid So the length of the the capillary height is found to be, let's say, 1.2 millimeters for a fluid which has contact angle equal to 53 degrees. Okay, now this capillary is gradually pushed in like this. Into the liquid, okay, such that eventually the length of the capillary outside it was initially L greater than 1.2 millimeters, as you can see, okay, reduces to L prime equal to 0.9 mm. Okay. So first of all, which of the following will happen? Liquid will continuously gush out of the capillary. Okay. The hydrostatic pressure just below the meniscus will become positive, the liquid will form a convex meniscus finally, or the liquid will form a concave meniscus finally. Second, find the contact angle when L prime is equal to 0.9 millimeters. So actually in this you will just have to select the correct option. Whereas the second part is a numerical part. The first part you have to just select the correct option. In this part, calculate the numerical value. Okay, now just one thing you should all understand, hydrostatic pressure at a point is basically what the pressure due to the liquid column. Okay, so what we mean by hydrostatic pressure, for example, is if you have, below a flat surface of liquid, a plain horizontal surface of liquid at a depth d, if you want to find the hydrostatic pressure at this point A, then the hydrostatic pressure is rho gh, whereas the absolute pressure is atmospheric pressure plus rho gh. Okay, this is the absolute pressure, whereas this is what we call the gauge pressure or the hydrostatic pressure. It is the excess pressure which is because of the liquid column. So that one at the point A is rho g d or whatever, rho g h if this distance is h. So that is what we mean by this. In the option B, that is what is meant by hydrostatic pressure. Yes, Somadeep appears to be correct. Yes, Bhumik, your answer also is correct. Okay. So see, the moment you understand the concept of pressure difference in the situation of this thing, in the situation of capillary action, you'll understand what happens when you force the capillary into the liquid such that the natural capillary height is actually more than the length of the capillary column which is above the liquid. So what happens is because of the what we call the difference in the adhesive and cohesive forces, okay, the liquid's junction with a solid interface, generally speaking, because the cohesive forces are stronger, it's like this. So there is a capillary, there is a contact angle which is positive. So what that creates is, so when you consider a cylindrical capillary like this, so what happens is that the liquid inside it, it forms part of a spherical shape like this, like it's part of a sphere. So this creates a pressure difference. Okay. So if the capillary has a radius of capital R, okay, but the spherical shape that is formed by the meniscus, the concave meniscus, that one, that has a radius which is small r, radius of curvature which is small r. So what happens is that between the point just outside and the point just inside, there is a pressure difference. PB is equal to PA minus 2T by small r. Okay. And now it's very easy to calculate the relationship between the contact angle and capital R and small r. If you take the two-dimensional view at the contact surface, if you draw a tangent like this and a tangent like this over here, these two angles are theta. Okay, that is a contact angle. Okay. And if you draw a normal and a normal over here, this is the center of curvature of the meniscus. Okay, so that angle is theta. So here, this angle is theta. So the relationship, and this distance is capital R. Okay. This is R over here. So you have R by small r is equal to cos theta. So then you have this, that this pressure difference is P at A minus 2T cos theta divided by capital R. So what happens is that the capillary rises inside the liquid. The liquid rises inside the capillary, sorry, in such a way that that pressure difference is compensated for by the capillary rise. Okay, so what is happening here is that if this contact angle is theta, this is formed a meniscus of radius small r, such that now this point is A, this point is B, and suppose this point is D and E. Okay, so what should happen is that the pressure at the point A will obviously be atmospheric pressure. Okay, and the pressure at the point E will also be atmospheric pressure. Okay, but the pressure at the point B will become pressure at the point A minus 2T by small r. So that is atmospheric pressure minus 2T cos theta divided by capital R, where capital R is the radius of the capillary, this one. Okay. In case of a cylindrical capillary. And pressure at the point D will become pressure at the point B plus rho g h, where h is this height now. So this is where we get that pressure at the point D is becoming P naught minus 2t cos theta divided by R plus rho g h. Okay. And that should be equal to pressure at the point E, which is nothing but atmospheric pressure. So that's why this term, this total term should become 0, and that's how we get that rho g h is equal to 2t cos theta divided by R, or h is equal to 2t cos theta divided by rho g R, which is the standard formula for capillary rise. Okay. So once you understand this mechanism, you'll also understand that what's happening in our case over here. यहाँ पे क्या कर रहे हैं? We are forcing the capillary into the liquid such that the length of the capillary above is not enough to create that pressure difference. Okay. So imagine, like, if you were doing this like an experiment. Okay. So initially, what is happening? There is air inside this capillary when you put it inside the liquid. So it takes some time for that air to come out. So as liquid is coming in because of the pressure difference. Okay. Now, as the liquid is coming in, it's inside also, it is at that contact angle initially of 53 degrees. Okay. So it's maintained this pressure difference. Now this H is not enough to make this point's pressure become equal to this point's pressure. So pressure at the point D is still less than pressure at the point E because this is creating too much of pressure difference. So liquid continues to rise inside. So like this, the liquid continues to rise all the way till it reaches the top now. And even then with the natural contact angle of 53, there is too much pressure difference across the meniscus for the height of the liquid column to be able to compensate. So what happens that even when this meniscus, if it were of that natural angle 53, then the pressure at this point just inside, let's say B, is lower than the pressure, atmospheric pressure, by such a large amount कि ये जो rho g h है वो उसको compensate नहीं कर पा रहा है. So this thing is just not happening. The pressure at the point D is still less than pressure at the point E for the contact angle equal to 53 degrees when the length of this has become equal to how much? 0.9 mm. Because we saw that for 53 degrees, for 53 degrees contact angle, the height was equal to 1.2 mm. So in this condition only, your pressure at the point D was equal to pressure at the point E, which was atmospheric pressure. So for this, it cannot happen. So now liquid will push further. So as it pushes further, it changes the shape of the meniscus. So the meniscus is going from a more deep shape like this to a more shallow shape like this. Now the meniscus is becoming this. So as a result of that, the contact angle will change. The contact angle will become some new value, let's say theta prime. Okay, such that this condition, so at theta prime which you want to calculate, the pressure at the point D should become equal to the pressure at the point E. So that means what should happen? The pressure at the point D plus rho g into 0.9 mm should be equal to atmospheric pressure. And the pressure at the point B, we've just seen is how much? It is atmospheric pressure minus 2t by the new radius of curvature. Okay. Okay. So now we can solve this and find the new angle of contact. So this is P naught minus 2t cos theta prime divided by capital R minus, plus rho g into 0.9 mm should be equal to P naught. So this is showing us that our cos theta prime is rho g into 0.9 mm upon 2t. Okay. So this is our equation 1. Whereas the original data, what it was showing us, the original data was showing us this, that cos theta, which was cos 53 degrees, was equal to rho g r into 1.2 mm divided by 2t. So we'll compare these two equations now. There is an r also here. So just divide the two equations. So you'll get the ratio of cos theta prime and cos theta, and from that you will get theta prime. So just now go back to this relation here and divide the two equations. So you can see that cos theta prime upon cos 53 degrees will be equal to, how much is it now? 0.9 upon 1.2. So that is 3 by 4. So theta prime will become cos inverse of 3 by 4 into cos 53, which is 3 by 5. Yeah. So theta prime is equal to cos inverse of, uh, actually I gave you the wrong value. I should have taken 37 was initially. So anyway, so then it's 4 by 5 plus 3 by 5. Anyway, doesn't matter. So 9 by 20, or theta prime has become cos inverse 0.45. Okay. So that you can see will be less than 30 degrees. So the contact angle has, sorry, greater than 60 degrees. The contact angle has increased, and that's what happens. So the thing is now, when the capillary was already in the position where initially L was greater than 1.2 mm, so it was in this situation I'm showing above. So here this L was greater than, it was in this kind of position. L was greater than 1.2 mm and H was equal to 1.2 mm with a contact angle of 53 degrees. So here it has achieved that equilibrium. Now from here we are pushing it, we are forcing it down. So initially some liquid will come out, obviously, because the volume of liquid inside the capillary is more. But eventually it will settle into this new kind of equilibrium where it will be a concave meniscus from when you see from above, but it will be comparatively having a lesser radius of curvature compared to this one. So what will happen is that when you push it down, on pushing the capillary into the fluid with L prime equal to 0.9 mm out, okay, it will still have a concave meniscus, but with radius becoming greater, this R prime becoming greater than R, and contact angle also accordingly increasing compared to theta. Okay, so that is why the correct options, I'll go back to that. Yeah, so this is about 63.3 degrees. So this will become about approximately 63.3 degrees. So the contact angle you can see is increased from 53 to that kind of value. So the correct option here will be this concave meniscus, and this will become cos inverse 0.45 or 9 by 20. Okay. Achha, now let's also see about this hydrostatic pressure. So the hydrostatic pressure at the point just below the meniscus. Na? So hydrostatic pressure at that point is what? It is the relationship with atmospheric pressure. Na? So this point is A and this point is B. At B, the absolute pressure is P naught minus 2T by R. Okay. So therefore, the hydrostatic pressure is negative, na? Minus 2T by R. That's why liquid is rising inside. So this is the gauge pressure or hydrostatic pressure. Okay. It's basically the value of pressure with respect to the reference value of atmospheric pressure. So if it is more than atmospheric pressure, then it's a positive gauge pressure. If it is less than atmospheric pressure, it's a negative gauge pressure. So another way the same question could have been asked is the pressure at the point just below the meniscus going to be larger than atmospheric pressure or lesser than atmospheric pressure? So that's why the answer is that it should be lesser than atmospheric pressure. So it should be negative. So that's why this positive is incorrect. Okay, so hope this is clear to all of you. If there's any doubt in any part of this, please discuss with me or let me know. I'll explain again. Shreya, this is clear now, beta? Okay. Okay, let's move on to another question. Okay, next up, we will look at a question related to excess pressure inside a air bubble. So we have two soap bubbles. They are of radii 3 millimeter and 6 millimeter. Now they come in contact. So when they come in contact, what we'll do is we'll assume that they do not break. So they come in contact here in such a way that they don't break. So for the common wall or the contact surface, the one shown by a dotted line, we have to first of all figure out whether the shape will be concave or convex when seen from the left. Okay. Is the shape flat or concave or convex from the right side? Okay. And the radius of curvature. So this common wall, which I have just left as a gap over here, shown by a dotted line. So we have to show that for that dotted line, what will actually be the shape of that common wall or that contact surface. And by the shape, I mean whether it will be a flat surface, no, like a plane surface with infinite radius of curvature, or will it be convex from seen from the right or concave when seen from the right, and what will be the radius of curvature in millimeters. Okay, so hope the question is clear. We'll finish this, then we'll discuss a couple of questions in viscosity, then I'll be coming to your doubts. Viscosity and drag force. Okay, radius of curvature will be different from the answer you people are giving. Okay, that is Somadeep. Okay, Bhomik, your answer about the shape is correct. Radius of curvature. So let me give you a bit of hint. You know, यहाँ पे the air inside is suppose at a pressure PA, और यहाँ पे the air inside is at a pressure PB. So PA is how much it is atmospheric pressure plus 4T by RA. You know, because it's a double walled bubble. It's a soap bubble, so that's why pressure inside B is atmospheric pressure plus 4T upon RB. So you can see that because RB is greater than RA, so therefore the pressure inside A is more than the pressure inside B. Okay. So now always across a surface, the pressure is higher on which side? It's higher on the concave side. So the wall here will be concave in shape so it will be convex from left and concave towards A. So the wall will be like this. So that PA is greater than PB now. So that's why. Okay. So this pressure difference should be equal to 2T divided by the new radius of curvature across. So this surface has some different radius of curvature. It has a radius of curvature, let's say like this. Sorry, 40. My mistake. Yeah, this is also 40. That's correct, Samudhi. This should also be 40. Because you still have air inside and just double walled film of liquid. Achha, using this only you're getting 6 mm. Samudhi. Let me check. So anyway, this is your equation 1 and this is your equation 2. Okay. And this is your equation, sorry. So PA minus PB is equal to 4T by R. Okay. This is your equation 3. So we'll more or less substitute the same pressure. There is going to be slight difference in volume, but we'll neglect that. We'll assume that the pressure of the air inside A and B remains the same. Okay. So 4T into 1 upon RA minus 1 upon RB should be equal to 4T upon R. Let me just check the value. Okay. Oh yes, it will come out to be the same. That's correct. My mistake. It will be the same. R will be 6 millimeters. Yes, that's correct. 6 millimeters. Okay. So hope this is clear. Okay, next example. So we have this situation on a rough horizontal surface. We have a thin film of some kind of viscous fluid. So we have a viscous fluid of coefficient of viscosity eta, okay, and its height is h. Now on that we have like a thin chipboard or cardboard piece or something which is floating. So it's almost massless. So thin rectangular cardboard sheet floating. Okay. So consider almost massless, and it has, say, this kind of dimension, 6 millimeter into 2 millimeter. Now what we want to do is we want to push it with some force, okay, such that it moves forward at a constant velocity v0. So find the force F needed to push the cardboard sheet at a uniform speed of v0 equal to, let's say, 5 meters per second. Okay. I'll just give you the value of coefficient of viscosity also. Just give me a moment. So let's take it eta for this liquid eta is 0.75 in Pascal seconds or Newton second per meter square. Oh yes, sorry. H also has to be given. H is 2 millimeters. This height H is 2 millimeters. Okay. Somadeep, your answer is correct. Hello. Okay, people. So let's understand this question. So what we'll assume is that the liquid, the viscous liquid goes into a laminar flow, right? So what happens is that if you imagine the liquid layer now in laminar flow, at least in the region where this thing is present, the region where the cardboard sheet is present, just under it over there, it is more or less in a laminar flow, such that the cardboard along with the layer of liquid in contact with it is moving at the velocity of v naught. Whereas this will be the assumption that because the surface below is rough, the velocity of that point will be tending to zero. So that laminar flow will have a velocity gradient which looks like this. So if this is your y-axis, your delta v by delta y will be more or less equal to minus v naught by h, where h was this height. Okay. So now on this surface from below, there will be a viscous force which has to be balanced by the external force because its acceleration is zero. So that viscous force will be eta into a into this velocity gradient. So the external force will have to balance the viscous force. It will be eta this into this. So now it's pretty simple. Just have to substitute the values. So coefficient of viscosity was 0.75 in SI units. Area will become how much now? 12 into 10 raised power minus 6. Okay. And this delta V by this will be 5 divided by 2 into 10 raised power minus 3. So this should be the answer in newtons. So 0.75 is 3 by 4 into 12 into 5 by 2 into 10 raised power minus 3 newtons. So 3/4 of 12 will be 9, 45 by 2. So 22.5 millinewtons. Moving the role of the rough surface is that it will ensure that there is sufficient friction between the surface and the liquid, that the liquid at the bottom will remain at rest. Otherwise, the laminar flow could have been such that the velocity profile could have been like this one. The velocity profile could have been like this. So the rough surface that is given during the question, and that's just like a hint to you that assume that the laminar flow has a velocity profile like this. So these kind of things are a bit approximate. Actually in reality the liquid will not have a perfectly uniform velocity gradient like this. Okay, because it's not like the entire surface of liquid is moving from the top. Right? It's only where the cardboard is present. So there's bit of approximation involved in this calculation, but we have to take those assumptions in mind while solving because we have only those kind of equations to solve. You cannot actually do a physical modeling of the whole situation and take care of the other things. Right. So hope this is clear. Bhumik. Okay. Good. Let's move on to one question which has that the tricky formula of the Poisson's equation. Okay, that can sometimes be a little bit challenging. Let's discuss. So let's say we have a container, okay, but at the bottom of the container, instead of an orifice, we have a cylindrical tube like this. So we have this kind of situation. So liquid is present up to a certain height at this instant of time. It comes out from here. So this is of length L, and radius R. Okay. And this liquid has density rho, this height h, coefficient of viscosity. All this is given to us. Let's say the density is 2 gram per cc. The height of the liquid column is, let's say, 50 centimeters. Take acceleration due to gravity 10 meters per second square. And the coefficient of viscosity, let's take 0.6 uh, Pascal second, this kind. Okay. And the capillary kind of thing below, this has a length of, let us say, 4 centimeters and a radius of 5 millimeters. Okay. So we have to find the volume rate of efflux, okay, in let's say cc per second, cubic centimeters per second. So यहाँ से जो liquid will be coming out, what is the volume rate of efflux? And assume that the area of the vessel, cross sectional area of the vessel, is much larger than the area of the capillary, that is pi r square at the bottom. So I'll just give you a hint in case some of you don't remember the formula. The viscous resistance of a cylindrical capillary is given by the formula 8 eta L upon pi r to the power 4. And this is what you have to use, the viscous resistance concept and Poisson's equation. Okay. Okay, so about Poisson's equation, let's just quickly go through that thing. So it says that if you have a cylindrical capillary like this, through which liquid is flowing through, then the relationship between the volume rate of flow of liquid, okay, and the pressure difference. So basically, when a viscous liquid flows in laminar motion through this kind of a section, then it has a velocity profile like this, which you should know. The velocity profile is parabolic, like this. So if the center line is coming out with a velocity v naught, then the velocity of liquid coming out at a distance r above is given by this relation. V is equal to v naught. I mean, at a distance r from the axis, 1 minus r square by capital R square. Okay. And anyway, so now from that, what you do is the volume rate of flow, delta V by delta T, becomes V dA integrated. So that is this V into 2 pi r dr integrated from r equal to 0 to r equal to capital R. So anyway, this volume rate is equal to the pressure difference. That is, if the pressure here is P1, the pressure here is P2 divided by viscous resistance. So it is P1 minus P2 into pi r to the power 4 upon 8 eta L. This is the formula. So in this case, we don't have to worry about the above formula, these ones which I'm writing. Just have to understand the values here. So क्या हो रहा है यहाँ पे, this point and this point are the ends of the pipe, and liquid is coming out through this with that laminar flow. So this we will replace with PA minus PB, which will be rho GH. Okay. So the volume rate be equal to this rho gh upon the viscous resistance, where the viscous resistance is 8 eta L upon pi r to the power 4. So this will give us, when we substitute everything in SI unit, it will give us the volume rate in meter cube per second, that you can convert to cc per second or whatever. Yeah, that's correct. Okay. Yeah, Somadev, next after this, I'm going to discuss the doubts only. I had one more question to discuss about terminal velocity, but I think I will keep that for the next lecture. And because we need some time for discussion of the doubts also. So I'll be going through the doubts next. Now, this thing also, now you should just know as a formula. When you substitute this now, the relationship comes out like this: V naught into 2 pi 1 minus r square by capital R square r dr from 0 to capital R. So the relationship between the volume rate and the velocity of the axial point, that you should know. So delta V by delta T into this comes out to be r square. If you take common, get 1 by 2 minus 1 by 4. This kind of relation. So in case after finding the volume rate, you are also asked to find V naught, you can use this relation. So yeah, you will get the V naught by the volume is substituting the values. Centimeters, 2 gram per cc, 0.6. So this will give us a volume rate in meter cube per second. And then later you can see that 1 cc is 10 raised power minus 6 meter cube. So whatever we get in meter cube per second, multiplied with a million, you will get in cc per second. So you can find the delta V by delta T, whatever value. Now, in case you are also asked to find the speed with which the liquid is coming out, the maximum speed, you can also use this relation. Where V naught is the maximum efflux velocity or the cylindrical laminar flow. Okay, so this is clear, people. Okay, so next I'm going to start with the mechanics question which has come in for doubt from Somadeep. I will modify the question a little bit for discussion of a couple of other things in it also. Okay. So the question originally is like this, that you have a surface so it's a smooth horizontal surface on which chain is placed like this, such that one end of the chain is just about touching the floor below. Chain AB like this. So this height is h, and the chain's length has mass m and length L, uniform thin chain obviously. So we release it from this position. So at a certain moment the chain is set free. With what velocity will the end of the chain slip out of the table? Okay, so u is equal to 0 initially here. Now after some time, what will happen is that so Somadip, first of all, tell me what you try to do in this question. After you release the chain here, at a certain moment of time, the end is about here. This has a speed v, so we want to find out v. So what did you try to do? Achha, this is not your question. Whose question is this? Sorry. Okay. Yeah. Right. So anyway, so what should we try to do in this question? Yeah, Ayush, I'm coming to your question. Somadip, I'll come to your question also. I got it. Sorry. So you have a doubt in the 21st question or 22nd or 21st? Okay, I'll discuss. So anyway, let's discuss this one. So how will we find the speed VA over here? So when we release this chain here, by the time the end of the chain reaches this point A here, how will we find the speed? Or let me rephrase the question. Can we use work energy theorem? Okay, now Ganesh, then answer my question. The beads of the chain which are on the floor, what kind of collision are they making? Even if nothing is given in the question, now we cannot assume they are making elastic collision. Most probably they are making inelastic collision. So then they are non-conservative collision forces. So this is where you have to be very careful. So in this kind of situation, what is happening now? It's not going to be conservation of mechanical energy. So we have to apply dynamics basically. So to find speed, mechanical energy will not be conserved. Okay, so there will be dissipation of energy that occurs. Okay, so how we will do this is that we will take an instantaneous time when the chain is displaced by x, let's say. So A is displaced from its original position by some x. Okay, so this is h. This has become L minus h minus x. So at that point of time, now we will look at the dynamics. We look at the acceleration with which this is falling. So if the tension here is T and the tension here is T prime, so we can neglect the mass which is at the corner. So neglecting that small delta M mass at the corner, no? This delta M is being pulled by T prime on this side and T on this side. So delta M is tending to 0. So we can take T prime equal to T. Okay. So we will take the FBD of the part which is vertical of height h, and we'll understand that that part has mgh by L and T acting, and it has a downward acceleration E. So mgh by L minus T is equal to ma. Okay. And then we'll take the frictionless surface wala part. So on this, there is the same tension T acting from this side, and its length is L minus H plus X, this kind of length. So it's going to have the acceleration T is equal to M upon L into L minus H plus X into A. Second equation. Okay. So basically, you can just think of it like this. It's like this kind of situation. This has mass m2 and this has mass m1. Then the common acceleration of the system on a frictionless surface. So you can just do it without all these equations. You can see that this A is m2 upon m1 plus m2 into G. So here this A will be basically what? It will be the weight of the overhanging part, that is mh by L, divided by the total mass of this part plus this part, which is going to be m by L into H plus L minus H plus X. That is L minus X. It's very easy. It is m by L we can cancel. So H upon uh, L minus X, times G. That is your E. So A is your dV by dt, and V over there, you can see I had written in such a way that it was positive of dx by dt, because x was the displacement in this direction of the end of the chain. So V and A, like we can write like this. So A we can also write as V dV by dx. So your V dV by dx is equal to H upon L minus X into G. So the trick for doing this is, you can write this equation using this thing directly on this. You don't have to solve equation 1 and 2. Obviously, you can add them and solve and all that, but you can save time. Yeah. Yes, correct. That's good. Okay. So V dV is equal to Hg dx upon L minus X. Okay. Now your X is going from 0 initially to X equal to L. L minus H, because the chain was initially like this. So this was L minus H, this was H. When your U was 0, okay, so X was 0, and then it's reached here. So your X has become L minus H, and your speed has become V, or let's say some V final over it. So this V square by 2 or V final square by 2 is becoming GH into, now this will be ln minus ln L minus X, but when you put the limits and all that, you will get natural log of L upon L minus H. After putting the limits, adjusting the minus sign and all that, so you will get this V as square root of 2gh into this logarithmic factor. For example, if h is L by 2, that will be ln 2, that factor. So this whole thing to the power half. So this kind of V you will get. Okay. So this is an important question, and related to this is also a question of impulse momentum we'll discuss. Nahi, Somandeep, is that happening? See, lower limit x is 0 now. So this will be L, and upper limit x is L minus H. Correct. So it will be L by H minus H. Yeah, x is L minus h. So when you substitute L minus h, so this is basically minus of ln L minus x for the limits x equal to 0 to x equal to L minus h. Substitute all that, you will get this. All this inside the square root, remember. Okay, now in this same type of question, now one more thing you can be asked is the normal reaction contact force at this instant. So at the instant when the chain is here, can be asked the contact force, assuming that the beads of the chain don't bounce, that is, they make inelastic impact with the ground. So assuming inelastic E equal to 0 type of impact at the ground, so we have to find the normal reaction at the instant when the end A is at the corner. Okay, so end A has gone from this to this. So we just saw that V we had found out as square root of 2GH into natural log of L by H. So we have the V. Now we have to find this normal reaction. Samadhi, there will be one more term in that. Okay, I'll just give you a hint. Like the normal reaction will be like one term which is a weight factor, some mass into G, plus another term which will be like a lambda V square kind of term, mass per unit length into V square. Both are included. Acha, by L is outside the bracket. Yeah, yeah. Okay, okay. That's correct. Okay, very good. So here now, whenever we have this kind of situation that whether the chain is falling vertically without any table support or whatever, you have this situation where on a surface a chain is falling, making inelastic impact. We have to use the variable mass system concept, because if you apply Newton's second law to the portion of the chain which is on the floor here, it is a variable mass system. It's not a constant mass system. So at this instant t equal to t, okay, this has a mass, let's say delta m, okay, and this has a mass m minus delta m. I'm just explaining the general thing first, then I'll come back to this. Okay. So on this portion, if you see now, on this portion, you can see that the forces which are acting at this instant of time, t equal to t, is the weight of this portion, delta mg, and the normal reaction. Okay. But it's not that simple that n is equal to delta m into g, because at the next instant of time, okay, what is going to happen is that at t equal to t plus dt, this mass has increased to delta m plus dm, and this has decreased to m minus delta m minus dm. So it's like what's happening, there's a particle of mass dm which was moving down at a velocity v. This was at t equal to t, and now at t plus dt, that particle has got included in this. Okay, so this whole thing delta m plus dm is at rest now. But here what's happening, this thing was, delta m was at rest and dm was going down at speed v. So when we apply Newton's second law like this, that impulse or net force is equal to rate of change of momentum, or impulse is equal to change in momentum. You'll see here that going from here to here, the impulse is n minus delta mg into that time dt. This is the impulse in the upward direction. Okay. So this is equal to the change in momentum in the upward direction, which is dm into v. So that's how we'll understand that this n will become dm by dt into v plus the weight of the portion which is on the ground. It's okay. And further, dm is lambda into dy, let's say, where this is the y coordinate. Okay. So that's m by l into dy. So dm by dt itself is m by l into dy by dt, or m by l into this downward velocity v. Okay. So this becomes m by l v square plus the weight of the portion which is on the ground. So you can understand this as a formula only now. Every time you don't need to derive this when you're doing this question. Now the value of v can be different in different circumstances. Here it's that logarithmic term because it's falling off a table. But if it's just falling vertically, it will be like a square root of 2gx kind of term. Okay. If it's coming down a rough surface, like it's coming down a tabletop and the tabletop is rough, then there will be a more complicated expression. So the v will every time be determined by dynamics. Okay, like we have determined by the dynamics over here. But finally, the normal reaction, that will be substituted. So at this moment of time, in this particular question, क्या हो रहा है? My delta m at this instant when the end A has just reached here, okay, so the whole chain was, remember, m into L. So this portion's mass, delta m, will just become m by L into how much? L minus h. And this V is that logarithmic term. Okay, so we'll substitute that and get the answer. Okay, so this delta m is this much. So finally our answer is coming out to be what, that n will be equal to m by l into l minus h g plus m by l into v square, and v we had already seen was that square root of 2gh into ln of l by h. So ultimately ये ऐसा आ जाएगा है ना, if we take m by l into g common or mg by l we take common, so we will have this term, Somadeep, you've given it correctly, plus ln of L by H. Sorry, 2gh into ln of L by H. Two H into ln of L by H. Right, this is the answer you are also getting, I think. Yes. Okay. So yes, however. So there are a couple of more versions of this question that you should know how to do. One is, you can try this yourself later. This surface has coefficient of friction mu. So then in your FBD equation for acceleration, you have to make a bit of modification. So ये वाला portion में friction भी आ जाएगा and tension and E, और ये वाले portion में just tension and weight of that part. So you have to solve it that way. So you can try a variation of this question where there is friction also. Okay. And the simple variation of this is when the chain is just hanging vertically initially and you release it. U equal to 0, ये वाले position से release करोगे. So by the time this is displaced by x, so this is the easiest version of this. Your V becomes root 2 gx. Okay. And at that point of time, your normal reaction, if you calculate this version of the question, your normal reaction becomes 3 times mgx by L. Becomes 3 times the weight of the portion which is on the ground. So it's like 3 times delta mg, because that v square wala term gives you double of the weight of the portion on the ground. So these two extra versions of this question you can try out. Okay. So this is an important thing in application of impulse momentum and center of mass. Okay. Okay, now I'm coming to the biprism question, Somadeep. Okay. Let me just try and see if I can share the question itself. Yeah, so I'm just sharing the question first. So go through this question, everyone. Question number 21, I'll just explain. So the two position of the lens they are talking about now in the biprism experiment, this is somewhat similar to that determination of focal length by of convex lens by the optical bench method. Now, U and V for the two solutions are inverse of each other. Like reciprocal of each other rather than inverse. Okay. So I'll just explain. Okay, so let me explain the question. I'm going back to my whiteboard. breadboard now. Yeah, correct, Ganesh. Like displacement method for convex lens, that thing only. So, so displacement method for convex lens में क्या करते हैं? We have a source of light over here, and we have a screen over here, which is at a distance L, and we know that the focal length of the lens is such that uh, this L is less than 2f, that kind of thing. So we will get a situation where one position will be this, where we get the image on the screen. So if this is this, if this is x1 and this is x2, we'll get 1 by v minus 1 by u is equal to 1 by f. Okay, so in this case, v is equal to plus x2, u is equal to minus x1, and x1 plus x2 is equal to L. Okay, and we will get the second position where this same thing happens at this. They're like reciprocals of each other. Image for the same distance between the source and the screen, it will get a second position where we get the image on the screen. And that second position will be such that this will be x2 and this will be x1. So we'll have 1 by plus x1 minus 1 by minus x2 is equal to 1 by f. So as you can see, basically, we substitute like this: 1 by x minus or plus 1 upon L minus x is equal to 1 by f. This gives us a quadratic equation in x. So these two solutions of this now. So if the roots are alpha beta, then the two solutions are x1 equal to alpha and x2 equal to beta. So u equal to minus alpha and v equal to beta, or u equal to minus beta and v equal to plus alpha. These are the roots. Okay. So anyway, now we know that the sum of the roots is equal to L. Okay, and using that we can solve for focal length very easily. So when we write this quadratic equation, we have uh, x into L minus x is equal to FL, right? So x square minus Lx plus FL is equal to 0. So now we can see here that the sum of the roots is equal to L, and the product of the roots is equal to how much? FL. So from that we can find the focal length easily. Okay. So focal length becomes x1, x2 divided by L. Now when we solve, so that kind of concept now we will use in Fresnel's Bragg prism. So in Fresnel Bragg prism, as you know, the main situation you have is that you have a single slit. In front of that, you have put a biprism. And then you have the YDSC kind of setup, the screen very far away. So what happens is, what the screen is seeing is light coming from this, like this, as if it's coming from here. So like one virtual source here and another virtual source here. So the distance between the virtual sources is small d and this is capital D. Then the fringe width that we get is d lambda by d. Okay, that's the first thing. Now in the experiment, we actually, how do we measure d? Small d. Okay, so to measure small d, that is the distance between the virtual sources, S1 and S2, which are like virtual image, the single slit that you're seeing from this side. So from that side of the biprism, we use this method to measure this in front of this arrangement where the single slit is there and the biprism is there. You place a screen somewhere here. Okay. And then you place a lens here, a convex lens, and it will give you two positions at which you see the images of S1 and S2. So in one position, position 1, let's say, the images that you see, so S1 and S2 are like virtual sources here. So in this position 1, you are getting their images over here, S1 prime and S2 prime, okay, for position 1. So the gap between the images is, let's say, D1. Okay, and for that, this distance is X1 and this distance is X2. So you have this D1 by D is like the magnification factor, so it is X2 by X1. Yes, that kind of thing. Like, if you have a lens and you have a point object here and you get the point image here, then this D1 by this D is magnification. No? So it's U by V, sorry, V by U. So that concept here. Okay. Now position 2 of the lens is, let's say, here. So if position 2 of the lens is also giving you the images here, then this distance must become X2 and this distance must become X1. And this time S1's image will be here and this time S2's image will be here, and the distance between them will be D2. Okay. So now D2 by D will become how much? X2 by, sorry, X1 by X2. Understood now, someone? Yeah. So that concept. So now you can see that from these, D1 by D is 1 upon D2 by D. So D becomes square root of D1 D2. So don't even need the focal length of the lens. So this is how we experimentally measure the distance small d between the two virtual sources. Okay, next time, Bhumik, I'm coming to your doubt. Samadip, is there any other doubt of yours which is pending from before? Okay. So just give me a moment. I will share that. Doubt from Bhumik. Yeah, let's look at this. So we have this solid disc which is mounted on the vertical shaft. The shaft is attached to a coil spring. So coil spring का concept क्या होता है, that it's like if it rotates to theta, then it applies a restorative torque of c theta. It's just like a torsional wire. When you twist a torsional wire, it applies a restorative torque. Like that, the coil spring also applies a restorative torque. Okay, so we'll discuss the second part, the new amplitude. So everybody just give this a try. Okay. So you have the disk of mass m and radius r, it's rotating about its vertical axis. So moment of inertia is mr square by 2. So undergo the two disks can undergo SHM and you can find the frequency of motion. Okay. Now what is happening? Disk is moving according to theta equal to theta naught sine omega 2t in part 1. Okay. And at time t1 equal to this, a ring. Okay, so we have a single disk only, no? Moving in this, we have only a single disk, right? Why is the question saying disks? We have a single disk, on that we are going to place a ring. Yeah, okay. Okay. So you have your disk which is already in SHM, which is having the phase constant 0 and omega, which we'll calculate in the first part, amplitude theta naught. Now at the instant of time, t equal to pi by omega, when basically the angular position will be 0. So that means it will be at mean position. So it will have maximum kinetic energy. That is when you are putting a sticky putty of mass m and radius r is a ring of sticky putty. Okay, so a ring of the same mass and radius is dropped concentrically. So new frequency, huh? So basically what is happening now, this is like that, it's an angular version of that question where a block is doing SHM and another block makes an inelastic collision with it. So to just do the angular version of that. So angular momentum will be conserved, but energy of oscillation will change, and angular frequency of oscillation will also change because moment of inertia is changing. Okay, so just like the linear question is like this, that if you had this spring mass system doing SHM, okay, so suppose this is M1, okay, and this is doing SHM right now with x equal to some E naught sine omega t, and omega is going to be square root of k by m1. Now when it is at the mean position, let's say x equal to 0, this is moving with v max equal to that a naught omega. Now at that moment, let's say you drop a sticky mass m2 onto this. So what happens? Its momentum remains conserved just at that moment when the sticky mass gets attached. So this velocity changes from a omega naught to it changes to some v prime. Okay, but x is 0. So the energy changes, but momentum remains conserved. So m1 plus m2 v prime becomes equal to m1 a omega or a naught omega. That's your first thing. Okay, and now what will happen? This v prime will be your new amplitude into your new omega. Okay, and your new omega will be what? Square root of k upon m1 plus m2. Okay, so this is your second thing. So that will tell you the amplitude using this relation. So understood now, Bhumik? Now we have to make an angular version of this. So in the angular version, your disk, which has mass m, radius r, is already spinning because of that coil spring. Okay, so it is doing angular SHM with theta equal to theta naught sine omega t. Now in this, what is my omega? So your torque is equal to I alpha. So torque will be c theta into mr square by 2. Moment of inertia is mr square by 2 into minus d2 theta by dt square. So that's your angular harmonic motion equation, dynamic equation, that it is minus 2c upon mr square theta. So your omega is square root of 2c upon mr square. This is what is happening initially. Okay. Now as this is happening, you're dropping that. So at the instant when theta is 0, okay, so therefore d theta by dt is maximum. Okay. So not to confuse that with omega of SHM. So that's why I'm writing it as d theta by dt is maximum. So that is how much? Theta naught omega. Now at that moment you're dropping onto this that putty ring. of mass m and radius r. So next instant what will happen? This and this will rotate together. The disk with the ring attached to it. This system will rotate together and about this axis. So it will have some new value of d theta by dt. Okay, theta is 0 at that instant, but that d theta by dt will be such that your new I, that is I1 plus I2 into this new value of d theta by d2 should be equal to your original I into theta naught omega. So this will be mr square by 2 plus mr square disk plus ring into the new value of this should be equal to mr square by 2 into theta naught omega. And this new value of d theta by dt, let's just write it with prime sign. Okay, this is going to be how much? Your new angular amplitude into new moment of inertia into new omega. So 3 by 2 mr square into new angular amplitude into new omega should be equal to mr square by 2 into original angular amplitude and original omega. Now what is going to be a new omega? It is going to be uh, c divided by the new moment of inertia. No? So that was 3 by 2 mr square. C divided by m by 2 plus mr square. So this is going to be 2/3 of c by mr square. So I mean square root of this. Omega square is this. So my omega prime is how much? 1 by root 3 times omega. So we'll substitute this one. Bhumik, you're following this, beta? Okay, so that's all we have to do. Now we have to substitute this. So 3 times theta naught prime into omega prime. Now omega prime is 1 by root 3 times omega is equal to theta naught into omega. So your new angular amplitude, according to my calculation, as long as I've not made any mistake, it should be this. Okay, so there is conservation of angular momentum for the system. Okay. So I1 into that, d theta by dt max jo tha, that will become I1 plus I2 into the new value of d theta by dt max. And then we are using that trick that d theta by dt max is equal to angular amplitude into angular amplitude into angular. So this is equal to theta naught into omega, whereas the new value of d theta by dt max, it becomes the new value of angular amplitude into new value of angular frequency. And angular frequency is c divided by I. I mean square root of c divided by I. When you have a torsional pendulum or torsional wire or a coiled spring, that kind of situation, the c is that constant. Okay, so hope the question is clear now, Bhumik. Okay, Ashwin, I'm coming to your doubt next. Ayush, you also have doubt? Yeah, just a second. Just give me a moment. Don't worry, we have a lecture on Wednesday, so be confident we can finish off all the doubts this week. Okay, let's come to this. So we have a circular wire of radius r. Ayush, I think this is your doubt, right? Carrying current I in the horizontal plane. So this is that thing, no? You just compare this with a magnetic dipole, no? So what you do here is this circular loop that you have. I and radius r, you compare it with the magnetic dipole. Sorry, mu. So the magnetic dipole moment, if the current is anti-clockwise when you are seeing from above, it's pointing like this. So that mu is how much? I into pi r square. Now you find the formula for this thing at an equatorial point and at an axial point. Okay. So if at the equatorial point the distance is L, and L is very large compared to the size of the dipole, then what is the formula for magnetic field? B1, and here the magnetic field will be B2. This is L. So just remember, for electric dipole formula कैसा होता था? For electric dipole on the, sorry, here the direction of the field will be opposite than what I've shown. At the P2 point, the direction of the field will be like this. Oh, sorry guys, I was on mute. Okay, somehow got muted. So this is the master formula that you should remember. And this radial and tangential position, sorry, rather axial and equatorial position, these are like just special cases of this. Okay. So at this point, this is your r cap direction, this is your theta cap direction, but your theta is 90 degrees. Okay, and your r is equal to y. So your radial component becomes 0 and your tangential component, this thing, Kp divided by y cube. So your net field at this point will look like this. Okay. So this is your what we call the equatorial point, and this is what we call the axial point. Okay. So this electric field has a value of Kp by y cube, and this one here has a value of 2 Kp by x cube. Okay. So this is the two special cases, whereas this is the general equation. So now every time you have a current carrying loop like this carrying current I, and you want to find the magnetic field at any general point also, you can find the radial component of magnetic field and the tangential component of magnetic field using this. You just replace this with a magnetic dipole, and this angle is theta and this distance is r. So your thing is the same. Your radial component of magnetic field will become 2 times mu naught by 4 pi into mu cos theta by r cube, and your tangential component will become, sorry, mu naught by 4 pi into mu sine theta divided by r cube. Okay. And one more useful formula from this is then your net field is this. So if you want to find the magnitude of the net field, that also comes out to be like this: Kp by r cube square root of sine square theta plus 4 cos square theta, which you can also write as 1 plus 3 cos square theta. I'll just magnify. I'll share the document with you, so don't worry. This is visible now, beta? Okay, okay. Okay, people, so we'll conclude today's session here. Bhumik, there's one more question now of yours which you have, sorry, not Bhumik, Ayush, there's one more question of yours which you have sent with the two magnets now. So that also you can do with the formula of potential energy of two electric dipoles, जैसा होता है ना? Like that you use a formula for the potential energy of a two magnetic dipole system. So we will discuss that on Wednesday. Day after tomorrow, I think we have one more lecture. We'll discuss that and other questions. Okay, but you can try it out by that method. That anytime you want to understand the interaction between two dipoles, you have a formula of potential energy of interaction of two dipoles, and you can differentiate that, or the gradient of potential energy is internal conservative force. That kind of concept you can use. So that's it for today's session, people. We will discuss the rest on Wednesday. So keep sending me your doubts also. I'll select some questions from the doubts for Wednesday then.